So neutrons, right? They get a bad rap. Everybody's always like neutral subatomic particle. Who cares, man? I mean, protons, positive charge, electrons, negative charge, electrons are bonds and all that stuff. We like never talk about neutrons. So what are they even there for? Why even have them? Who cares? Okay, well, neutrons stabilize the nucleus. By adding mass to the nucleus, they help stabilize it. And there are only certain combinations of protons and neutrons that are stable. Um, and if the combinations of protons and neutrons are unstable, then we say that that atom is radioactive. It's a radioactive atom. Um, Combinations of protons and neutrons that are stable are not radioactive. A radioactive atom is just another term for an unstable atom that will eventually decay and release some energy and become something hopefully more stable in the end. Um, how can you predict if a combination of protons and neutrons is stable? Well, if you make a graph of mass number versus, protons versus neutrons, there is a trend. We call this zone here where the stable nuclei fall. We call that the zone of stability. If your combination of protons and neutrons falls outside of that zone, then you're going to be unstable and you're going to be radioactive. It's important to understand, when you hear radiation, you immediately think man-made bad, right? But radiation is a natural phenomenon. Radioactivity occurs naturally on Earth. There's radioactive decay inside the Earth's core. It's part of the reason why it's so hot in the Earth's core, right? That heat is what causes geysers to happen, right? Or, hot springs or whatever. Um, let's see. Radon gas. So in this area specifically, in the Susquehanna Valley, we have a lot of limestones, a lot of radon gas. Radon comes up. It's a radioactive, unstable, noble gas. And if you breathe it in and it's in your lungs when it radioactively decays, it can emit alpha particles and bounce around in there and, increase your likelihood of getting lung cancer. So, yeah, radiation, natural phenomenon. There are a few ways that atoms can radioactively decay, and we're only going to talk about three of them in this class. We're going to talk about alpha particle decays, beta particle decays, and gamma ray decays. An alpha particle is the heaviest of the particles. So there's the symbol for it, and here's its nuclear notation. An alpha particle is just a helium nucleus that is ejected from an unstable atom to try to make that atom's nucleus more stable. It does have a positive 2 charge because it's a helium nucleus, but we don't mess around with charges when we're doing nuclear chemistry. So when we do a nuclear reaction, you don't have to worry about electrons in those transformations, but it is a positively charged particle. It's not neutral. You should have heard about alpha particles before in Chem 101. This is what Ernest Rutherford uses to discover the nucleus in his gold foil experiment. He fired alpha particles from a radioactive chunk of radioactive material to discover the the nucleus. A beta particle, here's our symbol. Here's our nuclear notation, 0 minus 1e. A beta particle is just a really fast-moving electron that gets ejected, and it changes the number of neutrons and protons in the nucleus. Yeah, that's another way for an atom to hopefully become more stable. And then a gamma ray, which you should have heard about in the Chem 101 when you were studying light and the hydrogen atom. Gamma rays are the highest energy form of electromagnetic radiation. A gamma ray is just a beam of light, and it has no mass number and no atomic number, so it's a 0 over gamma, which we usually just do like an upside down fish. There's your gamma. That one looks kind of fancy because it's text, right? So gamma rays are neutral. So alpha particles are a helium nucleus. They have a positive charge. They are the largest of the atomic particles. Beta particles have a negative charge because they're just an electron, and they're in the middle when it comes to size. And gamma rays are neutral, and they are the tiniest. This is actually just a photon of light which is that wave-particle duality thing. So very, 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 very tiny. On this next slide, I always say picture's worth 1,000 words. So we got two pictures here. Let's look at this picture on the left. So inside this lead container with a hole in it, we have a radioactive material that is releasing alpha, beta, and gamma, and it's being fired through this horseshoe magnet. So what is this picture trying to show? Well, this picture is trying to show that alpha particles and beta particles have a charge. So if you imagine the north end of this magnet being like positive and the south end of this magnet being the negative magnetic field, the beta particles are attracted to the positive, the alpha particles are attracted to the negative, and the gamma rays just go straight through. They're not deflected by charge. So this is to show you the charge. And then this picture over here is to show you the size. So alpha particles are the largest. You can stop them with just a piece of paper. Beta particles are next largest or in the middle. You need a sheet of aluminum foil. So it's like in the movies, you get that crazy guy with the aluminum foil hat, trying to keep the aliens from stealing his brain waves. So I guess they're using beta particles to do that. I don't know. And then gamma rays, good luck stopping a gamma ray. You need 6 inches of lead or 6 feet of concrete to stop a gamma ray. It's pretty crazy how high energy they are. I mean, light just penetrates, so much. Inside a house, you can turn on the radio, pick up radio waves. Those beams of radio wave light are just passing right through your house, all the time. Cell phones, right? All the time, constantly. So they're so high energy, they can just go through matter. Cool. Transmutation is really the fancy term for what radioactive decay is. Transmutation is the general term for turning one element into another. And this is what alchemists, if you think about it, were trying to do. Alchemists were trying to take something that wasn't gold, turn it into gold. So alchemists were trying to take a cheaper, maybe metal, and turn that into a more expensive metal like gold, and trying to get rich quick. So transmutation applies to any event where you're trying to change one element into another. And radiation, radioactive decay, does that. That is a type of transmutation. When you think of radiation, you probably think of just high energy events, right? So where does all that energy come from? Why does radiation have so much energy associated with it? Why can it, mutate your cells and cause cancer? Where is that coming from? Well, it's really Einstein who explained where that energy comes from. In a radioactive decay or a nuclear fission or nuclear fusion, which we'll get to a little later, small amounts of mass are getting turned into massive amounts of energy. And that's because mass gets multiplied by the speed of light squared. And the speed of light is 300 million, 3.00 times 10 to the 8th meters per second. And then you got to square that. So think about it. You say, well, wait a minute. How can the tiny masses in the nucleus, right? I mean, we're talking about like a neutron. The difference between a mass between a proton and neutron is so small. How can that pack so much of a punch? Well, the answer is because you take this really small number and then you multiply it by 300 million squared, and you can see where that energy starts to come from. Okay, so that's Einstein's famous equation that I'm sure you guys have all heard of before, and now hopefully you understand what it means. It means small amounts of mass get turned into huge amounts of energy, and yeah, cool. So I want to practice doing some nuclear decay problems. This is really what's going to be on the test, is doing some of these decays. So if you have a periodic table out, you'll need it. I want to do this one, the alpha particle decay of americium 241. This reaction is happening right now in the room that I'm sitting in. I was just saying, don't worry, I'm okay. Okay, hopefully. This is what happens in smoke detectors. So I got a smoke detector right there on the ceiling. Inside smoke detectors, you got a small piece of americium 241, and it is constantly releasing alpha particles. And as long as those alpha particles are hitting the detector, smoke detector doesn't go off, right? Okay. But then some smoke gets in the room or a colloid, right? I mean, when we bought the house, the previous homeowner had the smoke detector in the hallway right outside the bathroom. Well, like in the winter, my son would like take a super hot shower and then open the door, and then that steam would come out and it set off the smoke alarm every single night, right? And only in the winter, right? Because the condensation was so intense then, because of the temperature difference. So I moved the smoke detector, right? Because I was tired of that happening. Never throw a smoke detector out, even if they're past their 10 years. Just take them to any waste disposal, and they'll take it for free, right? You don't want to throw a smoke detector in the trash because it's going to get smashed up, and that radioactive material is going to get out, and it's going to get in the groundwater. And it's going to make the groundwater radioactive. So please don't eat it. Anyway, enough about that. Americium-241. I want to predict and balance this nuclear decay reaction. So let me show you, and it does an alpha particle decay. So americium-241 doing the old alpha. Awesome. Well, let's find americium. Is down at the bottom of the periodic table. It is atomic number 95. So let's fill that in. Oops, missed the one. Atomic number 95. And now here's how this works. It's going to, we said, do an alpha particle decay. And an alpha particle is a 4,2-He. So that's one of my products. And I want to predict the daughter nucleus. So after an alpha particle flies out of this americium-241 atom, what's left behind? What's the daughter nucleus? Well, here's how this works. Okay, the sum of the mass numbers on the right side, the product side, has to equal the sum of the mass number on the left, in this case 241. And the sum of the atomic numbers on the right has to equal the atomic number on the left. Okay, so we can fill out the mass number for our daughter nucleus. What plus 4 is 241? Well, that's going to be 237. And then what plus 2 is 95? That's going to be 93. And then here's the awesome thing. Once you know the atomic number, you can go to the periodic table and say, hey, what element is this? This is neptunium. So the americium-241 up there in that smoke detector is decaying into neptunium-237. Iodine-131. Iodine-131 does a beta particle decay. This is if you have thyroid cancer or something. Thyroid cancer, knock on wood, is one of the easier traditionally cancers to treat, because you can give somebody radioactive iodine. The thyroid sucks it all up, and then it can, hopefully that it's like you're using radiation, which can cause cancer, using it to kill cancer, right? It's crazy. Yeah, so that is traditionally one of the easier forms to treat. Also, they can just go and remove the thyroid completely, and then usually people are okay. So anyway, let's talk about iodine-131. Iodine-131 does the old beta. And before we do anything, we should find the atomic number of iodine. So if you go to the periodic table, iodine atomic number 53. So 53. A beta particle is a 0 minus 1e. And this is the tricky one, folks. This is the tricky one. Okay, mass number doesn't change, 131. Atomic number, though, what minus 1 is 53? Be careful. I get a lot of 52s here. What minus 1 is 53? It's 54. And that, folks, is xenon. Xenon. So hopefully you're getting the hang of it, right? It's the sum of the mass numbers and the sum of the atomic numbers. And it's really that easy. Not that bad. And the last one here, we got sulfur 35 in the upper levels of the atmosphere doing a beta particle decay. So I would like you to try and write the balanced nuclear equation for that. Sulfur 35 undergoing a beta particle decay. Go ahead. All right, here we go. What's that sulfur 35 doing? Sulfur 35, sulfur's got an atomic number 16. A beta particle is a 0 minus 1e. Mass number unchanged, 35. Atomic number, 17. And that's fluorine, folks. Now, we didn't mention gamma rays. Here's why. A gamma ray can't really be predicted. Okay, we have to tell you that a gamma ray is also associated with an event. Because the gamma ray is 0, 0, okay, you can't predict it. It doesn't change the mass number, doesn't change the atomic number. I'd have to say something like, hey, with this iodine beta particle decay, not only does iodine 131 release a beta particle, but it also releases a gamma ray. If I said it also released a gamma ray, then that's where you would write the 0, 0 gamma over here and just showing that it's giving off additional energy in the form of gamma radiation. Yeah. A decay series, folks. The largest stable element, okay, in the universe is lead 206 or lead 207. It's an isotope of lead. Okay, lead is the largest. There's no atom above lead. So, like bismuth, for example, first one is there's no stable isotope of any element heavier than lead. So, a lot of these really big guys, like uranium 238 here, they undergo a slow, painful, long journey into eventually getting to something that's either lead or smaller than lead. Okay, and lead has an atomic number of 82. So here's the decay series of uranium-238, which is the radioactive isotope used in like breeder reactors. So the nuclear power plants they use in Europe, not in the United States. Here in the United States, we use uranium-235, which is the fissionable form. Anyway, you can see uranium-238 is an alpha, turns into thorium-234, and then that does a beta and turns into protactinium-234, and then that does beta and turns into uranium-234, and blah, 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 blah. Right? Eventually, you get all the way down to lead-206 in this case. I put an optional practice problem up on D2L that kind of has you go through this and predict it. I'll show that later tonight. You don't have to do it. There obviously you can take a shortcut. If I told you that it did 1, 2, 3, 4, 5, 6 alphas and 1, 2, 3, 4, 5 betas, you could do 6 times 4 over 2 and 5 times 0 minus 1, and you could take a shortcut. You wouldn't have to write the whole thing out. Although you could.